In this video, we're going to be talking about energy and momentum in a rotating object. So, similar to how if an object has velocity, it has kinetic energy, if an object has angular velocity, it has rotational kinetic energy, which is just 1/2 moment of inertia times angular velocity squared. So it's the same thing as 1/2 mv squared, except we replace the m and v with the respective rotational quantities. So any movement of an object can just be represented as either a rotational motion of the object or a translational motion of the object's center of mass. And translational motion just means the regular motion, in a straight line. And so if an object is both translating and rotating, its total kinetic energy consists of the sum of its translational kinetic energy and its rotational kinetic energy, which is 1/2 mv squared, where m is the mass of the total whole object, and vcm just means the velocity that the center of mass of the object is moving at, plus 1/2 I omega squared, which is the rotational kinetic energy. So here we have two examples of a bottle of something rolling down a hill. So here we have something, and as the bottle moves down the hill, it translates, and also you can see it's rotating. So this is an example of translation of the center of mass of the object plus rotational motion. So its total kinetic energy is 1/2 mv squared plus 1/2 I omega squared. So here we have a bottle of water moving down a hill, and as you can see, the water level does not change. So we can tell that this object is translating, but it's not rotating. So here the only motion is the translation of this bottle's center of mass. So its total kinetic energy is just 1/2 mv squared. It has no rotational kinetic energy. So if we have a constant torque that is applied to a rotating object while that object undergoes an angular displacement, that torque does work on the object, and the work is just the torque times the angular displacement, just like how work normally is force times distance. And the power associated with this work is just the change in work over the change in time, or equivalently the torque times the angular velocity, just like how power it can be represented as force times velocity for normal motion. So the angular momentum of a rotating object is the moment of inertia times the angular velocity, just like how the linear momentum of an object is mv. And so this is the angular momentum of a whole rotating object, and we can also calculate the angular momentum of a single point if we calculate it with respect to some origin. So here we have this point over here, and it's moving in a circle, and this vector is the momentum vector, mv. So we need to choose some reference point. This can be just a random point, or it could be the axis of rotation. So the angular momentum of this point is the distance from the axis of rotation to the point, times p, its linear momentum, mv, times the sine theta, which is the angle between this line and the momentum vector. So similar to how we came up with a lever arm to calculate torque, we can also define this L here as the perpendicular distance between the axis of rotation and the line on which this momentum vector lies. Similar to the line of action of a force when we are looking at torque. So since sine of theta times is just equal to this L, we can also represent the angular momentum of this point as mvL. And so linear momentum is conserved if there is no net force, external net force acting on the system. And so similarly, the angular momentum of a system is conserved as long as no external net torque is acting on the system. So here we have a 10 kilogram pulley with a radius of 0.1 meters, and it's 10 meters above the ground. And then we have this 5 kilogram block, which is 4 meters above the ground, attached to this pulley by a string. And so the block is released from rest and it hits the ground. And when it hits the ground, we want to know the velocity of the block and the angular velocity of the pulley, because as the block falls, the string makes the pulley rotate. So we do this using energy. So initially the system has gravitational potential energy of the block and the pulley. And so, however, in the final state, the pulley does not move. So its gravitational potential energy stays the same. So it will cancel out in our calculations, so we don't need to use it. So basically what happens here is the block's gravitational potential energy is converted into kinetic energy of the block plus the rotational kinetic energy of the pulley. So we have mgh, the potential energy of the block initially, equals 1/2 mv squared, the translational kinetic energy of the block, plus 1/2 I omega squared, which is the rotational kinetic energy of the pulley. So since we have two unknowns, v and omega, we can replace v in terms of omega by recognizing that this block is moving at the same speed as these points on the outer rim of the pulley. And so we know that the linear velocity of these points on the outer rim of the pulley is just equal to times omega. So then we can replace the v of the block in terms of omega. And then if we solve this by plugging everything in and solving for w, or omega, then we find that the angular velocity of the pulley is 62.6 radians per second. And then to calculate the linear velocity of the block, we just do times omega, again because it's moving at the same speed as these points on the outer edge of the pulley. So the linear velocity of the block as it hits the ground is 6.26 meters per second.